One single experiment by Isaac Newton set the stage for one of the single most useful tools in astrophysics. He was probing the structure of light, unaware that the same principles would later be used to decode the structure of the universe. Over the next few centuries, this technique evolved into a powerful analytical tool, one capable of revealing the physical, chemical, and kinematic properties of celestial objects by analyzing the light they emit, absorb, or reflect. Using this, we've determined that the universe is expanding. Stars can be classified into distinct types, and both our sun and most stars are composed primarily of hydrogen and helium. It has allowed us to infer the existence of an invisible component, dark matter that dominates galactic mass, and to understand that the most luminous objects in the universe, quasars, are powered by supermassive black holes. This has made it possible to detect planets orbiting other stars, analyze their atmospheric composition, and even search for biosignatures. It is also through this technique that we discovered complex organic molecules forming within interstellar clouds, molecules that may serve as precursors to life. These discoveries, which now form the bedrock of modern astrophysics, all trace their origins back to that single experiment with a prism. This is the story of spectroscopy. Around 1666, Isaac Newton conducted a foundational experiment to investigate the nature of light. He began by darkening his room and allowing only a single narrow beam of sunlight to pass through a hole in a window shutter. He then placed a triangular glass prism in the path of this beam. The prism projected the light onto the opposite wall, not as a white spot, but as an elongated band of colors. Newton named this colorful band a spectrum, from the Latin word for appearance. The prevailing theory at the time was that the prism itself colored the light. Newton, however, hypothesized that white light was not pure, but was instead a composite mixture of all the colors he observed. He reasoned that the prism was not adding color, but was simply separating the light into its constituent parts. He explained this separation through refraction, the bending of light as it passes through a new medium. Newton correctly deduced that the prism bent each color by a slightly different amount. Violet light was bent the most and red light the least, which caused the single beam of white light to spread out into its distinct colors. This experiment directly demonstrated that color is an intrinsic property of light. By showing that light could be dispersed and analyzed, Newton established the fundamental principle of spectroscopy. The next major step came in 1802 from the English chemist and physicist William Hyde Wollaston. He built an improved spectrometer that used a lens to focus sunlight onto a screen, and he was the first to observe that the solar spectrum was not a perfectly continuous band of color. Instead, he saw that it was interrupted by a number of fine, dark lines. Wollaston himself did not understand the physical origin of these lines, theorizing that they were natural boundaries between the colors. His work, while pioneering, set the stage for Joseph Fraunhofer, a German physicist, optician, and a master lens maker, who 12 years later would independently rediscover and meticulously map hundreds of these lines, which now bear his name. In 1814, using a spectrometer of his own design which was far superior to previous instruments, Fraunhofer independently rediscovered these dark lines. Not content with a mere observation, he embarked on a systematic and painstaking process of mapping their positions. He ultimately catalogued over 570 of these lines, designating the most prominent ones with the letters A through K, a nomenclature that is still used for some of them today. Fraunhofer's meticulous measurements and his discovery that the pattern of lines was constant for sunlight, but varied for the light from different stars, laid the very foundation of stellar spectroscopy. Although the true origin of these Fraunhofer lines as absorption features of chemical elements in the sun's atmosphere would not be understood for several more decades. The key to unlocking this puzzle came in 1859 through the collaboration of physicist Gustav Kirchhoff and chemist Robert Bunsen. Using a clean-burning gas burner invented by Bunsen, they observed that when different chemical elements were heated, they emitted light only at specific wavelengths, producing a unique pattern of bright lines, an emission spectrum, for each element. Kirchhoff then made the crucial connection. He demonstrated that if light from a hot, continuous source passed through a cooler gas, that gas would absorb light at the exact same wavelengths at which it emitted light when heated. He realized the dark Fraunhofer lines were the absorption fingerprints of chemical elements in the sun's cooler atmosphere. By comparing the dark lines in the solar spectrum to the bright lines of elements heated in their lab, they could identify the chemical composition of the sun. This was a revolutionary moment. For the first time, humanity could determine what the stars were made of, and the science of astrophysics was born. In the 1880s, precisely ruled diffraction gratings began to replace prisms, allowing for much more detailed spectra. The advent of photography meant that these spectra could be recorded on glass plates, creating permanent records that could be studied and compared. This enabled massive survey projects, most notably at the Harvard College Observatory, where Annie Jump Cannon and her team classified the spectra of hundreds of thousands of stars, leading to a temperature-based classification system that is still in use today. Spectroscopy is also a fundamental method for studying stellar motion. The key principle here is the Doppler effect. Just as the pitch of a siren changes when an ambulance moves toward or away from you, the wavelengths of light emitted by a moving object shift depending on its motion relative to the observer. If a star or galaxy is receding, its spectral lines shift toward longer wavelengths, a redshift. If it is approaching, the shift is toward shorter wavelengths, a blue shift. This effect allows astronomers to calculate the radial velocity of celestial objects with high precision. One of the most significant applications of this was in the 1920s, when Edwin Hubble used redshift measurements to show that most galaxies are moving away from us. More importantly, he found that the farther away a galaxy is, the greater its redshift. This relationship, now called Hubble's law, implies that the universe is expanding. It's not that galaxies are simply flying apart through space, but rather that space itself is stretching, carrying galaxies along with it. This was a major turning point in cosmology, providing strong observational support for the Big Bang model. Spectroscopy also played a central role in uncovering the presence of dark matter. When astronomers measured the Doppler shifts of stars and gas in the outer regions of spiral galaxies, they noticed something unexpected. The outer parts were rotating much faster than expected based on the visible matter alone. According to Newtonian gravity, such rotation speed should cause the galaxies to fly apart. The consistent rotational velocities, even far from the galactic center, implied the presence of an additional invisible mass component providing the necessary gravitational pull. This unseen component, now called dark matter, does not emit, absorb, or reflect light, making it detectable only through its gravitational effects. Spectroscopy provided the velocity profiles that made this discrepancy visible and helped establish dark matter as a central feature in our current model of the universe. In the 1990s, spectroscopy became a vital tool in a new domain, the detection of exoplanets. Although direct imaging of planets around other stars was extremely difficult, astronomers detected planets indirectly through precise radial velocity measurements of stars. By observing minute periodic shifts in a star's spectral lines caused by the gravitational tug of an orbiting planet, they could infer the presence of planets even if they couldn't be seen. This method, known as the radial velocity technique, confirmed the existence of hundreds of exoplanets. Spectroscopy's capabilities extend further. When a planet passes in front of its star in what is known as a transit, some of the starlight passes through the planet's atmosphere. The gases in the atmosphere absorb light at specific wavelengths, leaving characteristic absorption lines in the spectrum. By analyzing these features, astronomers can identify atmospheric components such as water vapor, methane, carbon dioxide, and potentially even oxygen. This method, known as transmission spectroscopy, is currently the most promising approach for probing the atmospheres of exoplanets and assessing their potential habitability. Although no definitive biosignatures have yet been found, this technique lays the groundwork for future discoveries. Spectroscopy has also helped us understand some of the most energetic and distant objects in the universe, quasars. When first discovered in the 1960s, quasars appeared as star-like points of light. but their spectral lines were extraordinarily redshifted. The extreme redshifts placed them billions of light years away, meaning they must be extremely luminous to be visible across such vast distances. Further spectral analysis showed that quasars are not stars, but rather the active nuclei of young galaxies. At the center of these galaxies are supermassive black holes accreting matter at high rates. As material falls inward, it heats up due to friction and gravitational compression, emitting intense radiation across the electromagnetic spectrum. In the 20th century, the field of spectroscopy advanced well beyond Newton's original studies of visible light. Astronomers came to understand that what we perceive as light is just a small portion of the full electromagnetic spectrum, which stretches from high-energy gamma rays and X-rays through ultraviolet, visible, and infrared light all the way down to low-energy radio waves. Each of these wavelength ranges provides different and complementary information about astronomical objects, and detecting them required entirely new types of telescopes and instruments. To capture this full spectrum, astronomers began building specialized ground-based and space-based observatories. Ground-based telescopes equipped with modern spectrographs now use highly sensitive electronic detectors, such as CCDs, to record and analyze light across optical and near-infrared wavelengths. Techniques like multi-object spectroscopy enable astronomers to simultaneously record spectra from hundreds of targets, such as galaxies in a cluster, by using masks or fiber optics to isolate light from different objects. Another technique, integral field spectroscopy, combines imaging and spectroscopy, producing a three-dimensional data cube where each pixel in an image has an associated spectrum. This allows detailed spatial and spectral analysis of extended objects like galaxies, nebulae, or supernova remnants. Space telescopes take spectroscopy even further by accessing wavelengths that cannot penetrate Earth's atmosphere, such as ultraviolet, X-ray, and far-infrared radiation. Instruments on space-based observatories like the Hubble Space Telescope, the James Webb Space Telescope, the Chandra X-ray Observatory, and the Herschel Space Observatory have been equipped with spectrographs tailored to specific regions of the spectrum.